of radius of convergence. Well, actually, I should say interval and also radius of convergence. So like in the early example, the interval of convergence refers to are those x such that the power series converges. In fact, you could even consider the situation where the power series is written as, now I don't have enough space, so maybe I would slightly adjust and write it here. So you can consider the same interval of convergence like the last example we indicate. So then this would be the points at which the series converges. And the radius of convergence refers to the length. So in this case, the interval of convergence, let me draw a picture. So this is going to be your A, and it turned out that this is going to be a point slightly before A, so it's minus R and A plus R. So everything in between these two values, the series will converge. So this is called the interval of convergence. And the length of R for this interval, half of it if you like, would be called the radius of convergence. Okay, so if we recall our earlier example, that geometric series, then the interval of convergence would be between minus 1 to 1. So this is going to be your interval of convergence. And then the width, between 0 and the boundary. So this is 1, this is called the radius of convergence. So the radius of convergence is 1, the interval of convergence is between minus 1 and 1. And then the second example, would have the radius, the interval of convergence is between minus 3 over 2 and 3 over 2. So this is this part, and then the radius of convergence, little r is going to be 1.5. So that's the radius of convergence. And in the case of the second example that we looked at earlier, because it converges everywhere, so then the interval of convergence would be the whole axis. So this is actually the whole real axis, R, and the radius of convergence is going to be infinite. because there's no bound. So we simply call the radius of convergence to be infinite. So there is this quite important. Here is one more example, which is quite the opposite. That is, if we consider the coefficient to be n factorial times x to the power n, where n goes from 0 to infinity. So this series looks like the first term is going to be 1 plus, and then n is equal to 1, so it's 1 factorial, and x to the power 1 plus 2 factorial x2 plus 3 factorial x to the power 3, etc. As you can see, the general coefficient is n factorial. So a simple test for the ratio test. So if you double check, which is going to be n plus 1 factorial x n plus 1 divided by n factorial x to the power n. So this would be equal to n plus 1 times mod x, and this is going to tend to infinity as n go to infinity for each x, no matter what x is, except for 0. The ratio is going to tend to infinity, and hence therefore bigger than 1. So it must diverge. So it's diverged everywhere except for x equal to 0. So in this case, if you look at the real axis, then you will see the interval of convergence is only one point, single point x equal to 0, and then in this case the radius of convergence would be equal to 0 because no other place that it would converge. So this is the situation with what we call the power series. So let's recall. So a power series is usually written into the form that is an infinite sum of an times x to the power n, or sometimes you can change x to x minus a, which refers to a translation by a unit a to the right. And then we look at a few examples. We introduce the idea of radius and interval of convergence, and then we saw this few examples like this. What is important in this is that we have a theorem which I refer to the notes, and the theorem says that, so this is on page 4. So this theorem says that if you have a power series like this, then there exists a positive number such that the series is converging everywhere between within the within this interval. So essentially, this is the reason why you have an interval of convergence. So essentially, if this is the x-axis, this is a, then you always have between a minus r and a plus r, and then everything in between, it must converge. So that's why you have this interval of convergence. And then the radius of convergence is actually the length of that. And if it happens that the radius of convergence is equal to 0, it means it doesn't converge except as a single point A. Or if the radius of convergence is infinite, which means that it converges everywhere on the real axis. So this actually requires a proof, but we would skip the proof because basically you can see this from the ratio test or the root test. Okay, so the next thing I want to discuss is that we're going to jump over a little these examples of Bessel functions, and then we go straight into part 3. So for that, we need to jump back to the writing of the notes. All right, so this is about the boundary points. Okay, so for this example, let's revisit. Let's look at the following examples, where you have minus 3 to the power n divided by root n plus 1 to the power x to the power n as the power series. Okay, so a ratio test quickly. Let me use a different notation, capital A n plus 1 and a n. So you would have minus 3 to the n plus 1, x n plus 1 divided by root n plus 1, which is plus 2, and then divided by minus 3 to the n x n divided by n plus 1. Okay, so let's look at this. And then we have, so when after you divide, you have 3x, and then you also have the root of 1 plus 1 over n, and then 1 plus 2 over n. A situation like this. So when n goes to infinity, this whole thing is going to tend to 3x. Okay, so then now you see that for the limit to be less than 1, we require x is between minus a third and a third. So therefore you see that the interval of convergence is minus a third to a third, and under the last example, every point between these two ends will converge. Moreover, the radius of convergence is going to be 1/3. Okay, all right, so that was already discussed. Now the question is, what happened if we consider the endpoints? If we plug in these 2 points into the power series, what would that be? And moreover, I would like to take this opportunity to introduce that since now that if you pick any x between minus a third to a third, that's the interval convergence, the series will converge. So this would actually defines a function, that works for x